This is the second lecture for substitution reactions. So just a quick review. In the first lecture of this section, we looked at unimolecular reactions, or SN1, where the overall rate of the reaction was dictated by the rate determining step, which is really the step that forms the carbocation. We also looked at the carbocation, or the reactant molecule known as the electrophile, and we also looked at the stability of the carbocation intermediate. Remember that tertiary more stable than secondary than primary. We also looked at the stereochemistry of these reactions, in that the product of these reactions are racemic if the starting material is a chiral molecule. Then we looked at the solvent, and we pointed out that the solvent here is really the nucleophile. So that's why it's often referred to as solvolysis. So these reactions are termed solvolysis because the solvent is typically the nucleophile. Then we looked at some examples of analyzing reactions that proceed by SN1. So let's look at today's lecture. In today's lecture, we look at the SN2 reaction, also known as the bimolecular substitution. So this is substitution, nucleophilic, and the 2 means bimolecular. So features of the bimolecular reactions. We'll first look at the effects of solvents on the reaction rate. Then we'll look at substitution in terms of the substrate. What are the requirements or characteristics of the substrate, also known as the electrophile? And then we look at the nucleophile. What are the characteristics that make for a good nucleophile? Then we look at the stereochemistry of these products. The stereochemistry here, as you will see, will be different from the stereochemistry of SN1. Here it's going to be inversion. And of course, we'll conclude by looking at some applications of this type mechanism. Okay, let's begin. So for the SN2, or bimolecular reactions, what happens here is our electrophile. This is the electrophilic carbon. Here's our leaving group. This carbon is partially positive because it's bonded to the leaving group, which is typically electronegative, and when it leaves, it takes these electrons here. For the SN2 reaction, the nucleophile, here the hydroxide anion, attacks from the rear of the leaving group, exactly 180 degrees from the leaving group. It forms a transition state. Notice the transition state here. It has a charge distribution of partial negative and partial negative because our reactant here is fully negatively charged. Another aspect of the transition state, as you know, is that it's a description of the bond forming and bond breaking as the reaction proceeds from reactant to product. So this is the transition state here. The transition state falls apart to give the organic product, which will be the leaving group and the organic molecule. We can state that differently using an energy reaction coordinate diagram. So here is our reactant, That's the electrophile and the nucleophile, both reactants forming the transition state as we have seen before, and then it goes on to products. You may recall that this gap here is the energy of activation, which relates to the rate of the reaction. Since this is a one-step reaction, also known as a concerted reaction, there are no intermediates, as we have seen before. There are no carbocations. It's just a transition state here and products. So let us look here at the effect of the solvent on this transition state and the energy of activation. So if we have a charged reactant, as we had before, so notice this is charged. Of course, you may have here a counter ion such as K+, just to make it a neutral molecule, but the nucleophile is indeed charged. This goes to the transition state, which now has a charge distribution. So this negative charge here is no longer on one atom, but it's distributed between the oxygen and the bromine, which is leaving. So this charge is now distributed throughout the transition state. What that means is that in red, if you should carry out this reaction in a non-polar solvent, so we can go from the reactant to the transition state here and then on to product. So this would be our energy of activation right here for the red. That's in a less polar solvent or non-polar solvent. If you should carry out this reaction, however, in a polar solvent, it would solvate this ion here, or the nucleophile, lowering it in energy, as you've seen here. So there is a lowering in energy due to solvation. It does solvate the transition state, but not nearly as much, because the charge is already distributed and a little more stable than a localized charge here. So in a more polar solvent, here is the energy of activation. You can see that's much higher than in a less polar solvent, so you would expect the rate of this reaction to be slower in a more polar solvent compared to a less polar solvent, as shown here in red, because we're just looking at the energy of activation. Let's look at another scenario. So here we have the nucleophile. In this case, it is neutral. It's not charged. And here we have the electrophile, which is neutral, not charged. So the same type reaction comes in, and this N, which is nucleophilic, since it's giving up the electrons to form this bond in the transition state, it becomes partially positive. Since the bromine is leaving and taking these electrons here, it becomes partially negative. So you can see that this is charged, but it's charge separated. So if you're looking at the energy profile diagram, what you'll see here is that both will be at the same energy level in a more polar solvent and a less polar solvent, because the reactants are not charged. However, in the transition state here, you can see here that the less polar solvent will not stabilize this transition state, because it won't solvate it as much as a more polar solvent, which is shown in black. So it's lower in energy. So as you can see here, the energy of activation for the more polar solvent here is less than for the less polar solvent here, because the more polar solvent is solvating this charge distributed transition state, lowering its energy, which means that there is less energy of activation, faster reaction. So you should be able to analyze reactions of this type if carried out in a more polar solvent or a less polar solvent in terms of the reaction rates. And just to refresh your memory, the reaction rate depends primarily on or exclusively on the energy of activation. Let us look at the substrate or the electrophile. So here's the electrophile for this reaction. Here, the nucleophile has to gain access to this carbon and come right in to kick this out here to give the product, which means that there has to be a lot of space in this region around this carbon for the nucleophile to gain access. As you can see over here, if we have methyl groups or alkyl groups here, it's crowding this electrophilic carbon. Whereas if this were hydrogen, much smaller, there's more space for the nucleophile to come in. So in terms of reactivity, the electrophile, if it has hydrogens, it's more reactive than an electrophile that has alkyl groups bonded to this carbon. There's more space for the methyl compared to a tertiary electrophile. So the order of reactivity for the SN2 reactions or the bimolecular is the methyl is much more reactive than the primary and secondary, and we often say that the tertiary is so crowded that the nucleophile cannot gain access to the electrophilic carbon and is non-reactive by the SN2 mechanism. Let us now look at the nucleophile. As stated before, the nucleophile has to gain access to the electrophilic carbon. So the nucleophile, or the ideal nucleophile, has to be small. So if you were to look at the reactivity of nucleophiles for SN2 reaction, small nucleophiles are much better than large nucleophiles. And that's hard to predict. In the book, it has a table of nucleophilicity, which is a measure of the size of nucleophiles in different solvents. But the bottom line is they should be small. One complication comes in though, based on the solvent. So let's look at fluoride negative, so F negative right here. Looking at the periodic table, you can see that F is a very electronegative atom, or is the most electronegative, so you would expect it to be extremely small. And it's nucleophilic because it has pairs of electrons that can be donated to form a bond. However, in a solvent such as methanol, as you can see here, it is protic and it is polar. So this is a polar protic solvent. It can solvate the fluoride anion, making for an effectively large fluoride ion in a polar protic solvent. We say that it is highly solvated. So the fluoride anion is highly solvated in a polar protic solvent such as methanol and, as you can imagine, water. However, if you should use a less polar protic solvent, a solvent such as DMSO, for example, or tetrahydrofuran. Let's just look at tetrahydrofuran. This is it. Now let's draw it better. So we have here this. So as you can see here, this is an oxygen, and there are no hydrogen bonded to this electronegative oxygen. So therefore, this is a aprotic solvent. So that this type hydrogen bonding here will not be possible. So in an aprotic solvent, this is not solvated as much. Therefore, the effective size of this fluoride ion is much smaller. So you can see here that the fluoride anion in an aprotic solvent is a better nucleophile compared to in a polar protic solvent. So the solvent for the SN2 reaction makes a big difference compared to that of the SN1 reaction. So here's a table of some of the aprotic solvents that are good for SN2 type reactions. Acetone. Notice again, 3 hydrogens here bonded to carbon, not oxygen. DMSO, 3 hydrogens bonded to carbon, not an electronegative atom. And of course, as we said, tetrahydrofuran is down here. These are good solvents for SN2 reactions. Let us now look at the stereochemistry of the reactant and product. As we point out, the nucleophile comes in from the rear of the leaving group, exact opposite, to kick that out, so to speak. So we'll have inversion. It's like, as you will see in the book, it's like flipping an umbrella on a bad, severe storm. So it flips, so we have inversion. Notice again, the solvent is acetone, an aprotic solvent here. So written differently, if you have a stereogenic electrophile, here's the stereogenic center, and of course, as you recall, there is a hydrogen back here. But the bottom line is, here is our nucleophile. It will come in exactly opposite from this and create an inverted product here. So the product is an inversion of stereochemistry for the SN2 reactions. So let's look at a practical example here. So here we have a chiral carbon, and notice it's secondary because it has 2 alkyl groups bonded to the OH. We know that OH is a very poor leaving group. As pointed out in the earlier lecture, we can convert the OH to a good leaving group by adding an acid. But if you should do that, you will create here a carbocation, which means that the reaction will be going through an SN1. But you do not want that because you get racemic mixture. In this case, you want an inversion. So here is a strategy around that. Tosyl chloride. Here's a tosyl chloride. So this OH here will react with this sulfur, kicking out that, to create this as another molecule. Notice the configuration here is retained because the reaction takes place only on this oxygen, not on that carbon. So this is a retention of configuration. Now here we have the SN2 reaction where this comes in and kicks this out as a leaving group to get an inversion. So if you happen to do a synthesis and you need 100% inversion here, here is a strategy, especially if you have a poor leaving group such as your OH. Another strategy here is to use SOCl2. So you can refresh your memory on that one based on the last lecture, in that this creates a very tight ion pair, so this comes back in to maintain retention of configuration, but putting a chloride here instead. So let's do a summary here in terms of the factors that affect the SN2 reaction. So the first thing is the mechanism. It's bimolecular. 2 molecules in the important step, and this case it's only one step, so it's a bimolecular reaction, and it's concerted because it happens in one step concertedly. So that is the concerted reaction. Let's now look at the electrophile. The electrophile, there has to be enough space on the electrophile for the nucleophile to come in, so the methyl electrophile, which has the leaving group, is more reactive than the primary, secondary, and of course the tertiary is non-reactive. Stereochemistry, there is inversion of configuration in going from the reactant to the product. The nucleophile has to be small and a weak base. I didn't emphasize that before, but you need a weak base, because if there's a strong base, there will be elimination, which we'll cover in the next section, in the next chapter of this course. The leaving group has to be good, and we can tell good leaving groups because they are weak conjugate bases. So don't forget here, a weak conjugate base is one that's pretty stable. The solvent has to be fairly non-ionizing and non-protic. So in other words, they cannot be a hydrogen that's bonded to an electronegative atom such as oxygen or nitrogen. And depending on the charges of the reactants and transition state, the solvent will have an effect on the overall reaction rates for SN2 reaction, because that will dictate that energy gap for the energy of activation. Okay, let's look now at the application of this knowledge combined with the previous information. So let's look at this problem. So for this reaction here, it was determined that the rho value, don't forget the rho value here is coming from the linear free energy relationship studies. Okay, turned out to be negative, notice negative, and a fairly large number, 3.89. But it changes slopes to positive. So now you'll have to reflect on the linear free energy relationship lecture and see and determine the importance of this. Also, it was determined that the isotope effect here, kinetic isotope effect for hydrogen deuterium, was 1.069 for the methoxy. So in other words, they did the experiment and put the methoxy group back here and determined the kinetic isotope effect to be 1.069. Your job is to rationalize a mechanism that is consistent with these results. So expect questions of this type. Of course, you've seen this type questions on the previous 2 exams, where you have to apply the knowledge that we have covered in these lectures to solving problems. So let's quickly go over the observations again before we start solving this problem. So the observation is rho value is negative, which means that there is a positive intermediate that was developed in the RDS for this reaction. So you can start thinking positive intermediate, you can start thinking carbocation, and you can start thinking rate determining step to form a carbocation. So you can start thinking SN1. On the other hand though, there's a change in slopes. If there's a change in slopes, that means that there is a change in mechanisms as a function of changes in substituents. The change goes from a negative to a positive. So if it's positive, rho, as we can see up here, it means that a negative charge or partially negative was developed in the RDS. So you can see in the second mechanism, or in the other mechanism, it's not SN1. So we'll have to determine what that could be. The last set of information here is the kinetic isotope effect for the electron donating group methoxy. Turns out to be, as we have seen here, 1.069. Based on the magnitude of this value, it seems to be a secondary kinetic isotope effect. And as you can see from the reaction here, there are no CH bonds that was broken, so it's not a primary kinetic isotope effect, because here's the CH bond, here's the CH bond again in the product. So the implication is that it's a secondary kinetic isotope effect, which would imply that it goes from SN3, or a carbon in the reactant, goes from sp3 to sp2 in the rate determining step of that reaction. Notice again, it's positive and not, well, it's a number greater than 1. So if it were less than 1, it would be an inverse secondary kinetic effect, but now it's greater than 1, so it's a normal secondary kinetic isotope effect. So let's see how we can interpret that. So it implies here, based on the rho value of negative and a large value of 3.09, which suggests a carbocation for that large negative value. So this bond breaks in the rate determining step to form a carbocation. In the fast step, the nucleophile comes in to form that. So this is consistent with rho value of negative 0.89 for electron donating groups. So all, if you look at the plot, the electron donating groups would be to the left and electron withdrawing groups would be to the right. So what I'm getting at here is, if you look at a typical plot here, it would look like this, where we have electron donating groups such as OCH3 over here, and over here would be electron withdrawing groups such as NO2. And of course this is the log of the rate, so log K, for example. So this would be your typical linear free energy plot, where it changes slope from a negative to a positive. So this part here would be consistent with this mechanism. Let's look at the kinetic isotope effect experiment here. It implies that this carbon here goes to an, which is now sp3 hybridized, that's a benzylic carbon, goes from an sp3 to an sp2. That's consistent with a normal secondary kinetic isotope effect. So that would be consistent with the observed or the measured kinetic isotope effect. Again, the same mechanism as here. So this SN1 mechanism that's shown here is consistent with this rho value and is consistent with the kinetic isotope and normal secondary kinetic isotope effect. Let's see how we can rationalize this end of the linear free energy relationship plot. So this would now be consistent with a negative transition state, or a partially negative transition state. So this SN2 mechanism would explain that. So this nucleophile is coming into this carbon while this is leaving. As you can see here, this is a negative and a negative, making this carbon here partially negative. So that makes sense, because if you had on this molecule here a substituent such as a NO2, let's see if we can draw that in. You can see that it is pulling electrons away from this carbon here, making this even more electrophilic, so making this reaction here a better reaction for this to occur, because it's reacting with a very more positive carbocation here, electrophilic carbon, compared to if it were a nitro group. So this mechanism is consistent here with this should be positive. Pardon me, I'll correct that on the overhead. So this should be, this rho value here of positive 0.6 is consistent with a negative or negative distributed transition state here for the SN2 reaction. So again, this is the mechanism that's consistent with the reaction shown here, with the linear free energy of positive 0.6. Notice again the magnitude is fairly small, so as you can see here, it's a charge distributed here across these carbons, and not a fully negative carbon sitting on this on this carbon here, not a fully negative charge sitting on this carbon here. So that's an example. I think that's the last one. So that is an example of the application of the knowledge that we've covered, the concepts that we've covered so far, and applying that to solving a problem given experimental information. So just to recap this problem here, we were given the linear free energy relationships, the experimental measurements. We were given the kinetic isotope experimental results, and we were given the reaction. Our job is to utilize that information to rationalize a mechanism that is consistent. Notice that is consistent with the experimental results, and of course also consistent with the rate determining step, which dictates the overall reaction here. Notice for this reaction here, we're not putting in a rate determining step per se, because it's just a one-step reaction. So that's why it's not included, but you can put it in if you want. So this is the last lecture on aliphatic substitution reactions. The next lecture will be on aromatic substitution reactions before we end this chapter. So look out for that. I'll try to get that out shortly. And so continue studying hard, and I'll keep you posted. Okay?